Welcome. So this video will give us an understanding of the atom and some fundamental laws in chemistry, laws that are really important in chemistry, that you need to understand them to understand what chemistry is about. So the video covers the fundamental laws of chemistry, the Avogadro's hypothesis, Dalton's atomic theory, the plum pudding theory by J.J. Thomson, and Rutherford's atomic theory. So this is the beginning of understanding the atom, and then in class we'll cover some later models of the atom. So what are these fundamental laws of chemistry? We have three important laws, or we have three fundamental laws of chemistry. And one of the most famous laws is the law of conservation of mass, sometimes known as the law of conservation of matter. It says that mass is neither created nor destroyed. For example, if you look at a chemical reaction like that, you have the reactant here, water, breaking down to hydrogen and oxygen. So if we have to follow the law of conservation of matter, if you count the total number of atoms here should be equal to the total number of atoms here. That's why you need to have a balanced chemical equation. So let us count. Here we have 2 times 2, 4 hydrogen atoms. Here we also have 4 hydrogen atoms. Here we have 2 times 1, we have 2 oxygen atoms. Here we also have 2 oxygen atoms. So the chemical equation is balanced, and it follows the law of conservation of mass. The second law is known as the law of definite proportion. So in this law, it says that a given compound always contains the same proportion of elements by mass. So a carbon dioxide contains 1 carbon and 2 oxygen. Always. So it's not gonna change. If you are here in Lewiston, it's alright. How does a carbon dioxide look like? Or it needs to have carbon and 2 oxygens. If you go to China, you ask them the same question, they should give you the same 1 carbon, 2 oxygens. If someone tells you that no, carbon dioxide contains 1 carbon and 1 oxygen, you know that that's not true. That is a different compound altogether. That is carbon monoxide. Then we have a third law, that is the law of multiple proportions. This law says that when 2 elements form a series of compounds, the ratios of the masses of the second element that combine with 1 gram of the first element can always be reduced to small whole numbers. What it means is that the ratio of oxygen in carbon dioxide and carbon monoxide is 2. Here we see in carbon dioxide we have 2 oxygen. In carbon monoxide we have 1 oxygen. So 2 over 1 is equal to 2. If you look at the ratio of oxygen in carbon dioxide and water, it will also give you a whole number ratio. So that's what the law of multiple proportion says, that we have this compound, and this compound contains these 2 elements. The ratios should be the whole number ratios. Now let's dig into an atom itself. One of the early theories of the atom was established by John Dalton. He was an English chemist. Actually, he was not a chemist, but he studied something to do with chemistry. What does his law say? Dalton says that each element is made up of tiny particles that are indivisible, called atoms. He did not coin the term atom. This term atom was coined by the Greeks, one of them being Democritus, the guy who introduced this idea of an atom. But Dalton popularized the idea of an atom because he was also doing experiment as an experimental chemist, while the Greeks were just using thought experiments. So each element is made up of tiny particles that are indivisible. Dalton's atom was indivisible. The atoms of a given element are identical. The atoms of different elements are different in some fundamental way or ways. So if we look at an oxygen element, anywhere it should have identical atoms. That's what Dalton's theory says. If we now compare oxygen molecule and carbon dioxide molecule, we see that the atoms, or if we compare oxygen element and carbon element, we see that oxygen and carbon element are different in some fundamental ways. That's what Dalton's atomic theory said. Another statement is that chemical compounds are formed when atoms of different elements combine with each other. A given compound always has the same relative numbers and types of atoms. You can see that this is similar to the law of definite proportion that we just discussed in the previous slide. Chemical reactions involve reorganization of atoms, but the atoms themselves are not changed in a chemical reaction. So when a chemical reaction occurs, carbon is still carbon. It doesn't matter whether it's in carbon dioxide or carbon monoxide. What changes is the connectivity. So carbon dioxide will have two carbon, both sides. Carbon monoxide will just have a single carbon dioxide will have two oxygens on both sides, one carbon. Carbon monoxide will just have a single oxygen and single carbon. But the oxygen is still oxygen, the carbon is still carbon. That's what this statement means. So this is the diagram of Dalton's atom. It is something that is indivisible. There's nothing inside it. It's just a ball of some kind. Now, this guy Avogadro did a number of experiments, and he has contributed greatly to chemistry. So he did experiments at some temperature and pressure. So these diagrams will describe some of the experiments that he did. So he took 2 volumes of hydrogen and 1 volume of oxygen, reacted them, they underwent chemical reactions, and he produced 2 volumes of water vapor. He said, alright, fine. Then he took 1 volume of hydrogen, 1 volume of chlorine, reacted them, he produced 2 volumes of hydrogen chloride. So he noticed something. In the first reaction, I have 2 volumes of water vapor. In the second reaction, I have 2 volumes of hydrogen chloride. But here I have 2 to 1 volume, giving me 2 volumes. Here I have 1 volume, giving me 2 volumes also. Then another reaction, 1 volume of nitrogen and 3 volumes of hydrogen. He found that he also had 2 volumes of ammonium. So he reasoned, why do I have 2 volumes in all these cases, in all these reactions? What is causing me to have the same volumes? So he concluded that, all right, although the reactants are different, but they are producing the same number or the same amount of gases as their product. That's why the volumes are the same. So, I think I can have a hypothesis from here. So he hypothesized that at the same temperature and pressure, equal volumes of different gases contain the same amount of particles. So if you see a gas, that is one gas that is at maybe 3 liters, and another gas that is at 3 liters, and if the pressure is constant, in both cases the temperature should be constant and the pressure should be constant. If you see one gas at 3 liters, another gas at 3 liters at constant pressure and temperature, you know that those 2 gases have the same amount of particles. That's what Avogadro's hypothesis says. If you have these conditions different, then the Avogadro's hypothesis does not hold. So this means that under these conditions, the volume of a gas is determined by the number of molecules present, not by the size of the individual particles. So if we have 2 gases, we have oxygen gas in one container. So let's say we have 10 molecules of oxygen gas in one container, and we have 10 molecules of ethane gas in another container. At constant temperature and pressure, it doesn't matter whether oxygen is bigger than ethane or whether ethane is bigger than oxygen. What matters is how many molecules of each do we have. They will have the same volume. Now let's practice. So which of the following is a statement of Dalton's atomic theory? So you can stop the video, think about it before I give you the answer. Here the answer is A. The atoms of a given element are identical. Another practice question. Avogadro's hypothesis says that at the same temperature and pressure, equal volumes of different gases contain the same amount of particles. This means that, so think about it, stop the video and think about the answer. In this case, the answer is D. Under these conditions, the volume of a gas is determined by the number of molecules present, not by the size of the individual particles. Alright, let's proceed. Dalton says that an atom is indivisible, but later experiments, later research found that no, an atom can be divisible, can be divided, because the atom has particles inside it. So what we are looking at is what is inside an atom. So J.J. Thomson used a cathode ray tube to understand the inside of an atom. So let's see if we can watch what Thomson did.
A cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the 2 metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes the specially coated surface, the cathode ray produces a strong fluorescence or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction.
So, what Thomson did was he applied a high voltage to this cathode ray and observed a ray that he called a cathode ray. So the ray that was produced at the cathode from here is repelled by the negative pole of the applied electric field. So this is the electric field that he applied. The ray is coming from the cathode here, passing through the anode, going all the way here. When he puts electric field on both sides, you see that the ray is repelled by the negative side. So he reasoned that if the ray is being repelled by the negative side, but we know that like charges repel each other, it means this ray this ray has also negative charges. So I will call these negative charges electrons. So from there I said, I think the atom has something inside it called electrons. Also, he used magnetic field. There was also an interaction, as we saw on the video, with the magnetic field. So okay, so an atom interacts both with electrical field and magnetic field, and it is being repelled by the negative side of the electric field, negatively charged part of the electric field, which means an atom has those negatively charged particles. So from there he developed a theory. But first thing first, he reasoned that alright, an atom has these negatively charged particles, but I know that an atom is neutral. So if the atom has a negatively charged particles, it must have positively charged particles also. But the major question was, where are these found? Where do you find these negatives? Where do you find these positives? So he came up with a plum pudding theory. So he concluded that since electrons could be produced from electrodes made from various types of metals, all atoms must contain electrons. So he assumed that atoms must also contain some positive charges because atoms were neutral. So from there he postulated that an atom consists of a diffuse cloud of positive charge with the negative electrons embedded in it. So like a plum pudding, you can see here. All this is a cloud of positive charge, and this is an electron, this is an electron, this is an electron. So the electrons are everywhere. This is a two-dimensional diagram of that, while this is a three-dimensional diagram of that. Discovery of an atom was accelerated also by the discovery of radioactivity, because by that time everyone was saying, alright, the atom is present as a plum pudding. But later experiments and also the discovery of the particles, the alpha particles, the beta particles, the gamma rays, in general, discovery of radioactivity helped us understand more about the atom. So Becquerel accidentally found that a piece of mineral containing uranium could produce its image on a photographic plate in the absence of light. So he called that radioactivity. Later experiments, gamma rays were discovered, and gamma rays are very important in understanding the electron. Oh, pardon me, not gamma rays, but the alpha particles were discovered, and the alpha particles are very important in understanding the electron. The alpha particles have a positive 2 charge, so we'll see why these are important. Gold foil experiment conducted by Ernest Rutherford. So Ernest used the alpha particles to understand what is inside an atom. So he posited, if Thomson is right, and I direct alpha particles at a thin sheet of metal oil, the massive alpha particles should crash through the thin foil like cannonballs through the gauze. So he reasoned that if I bombard alpha particles on a thin sheet of metal, the particles will pass through. They will not bounce, they will just crash through, and they will not bend, they will not change direction. That was his assumption. But then he did the experiment himself. After doing the experiment, he observed that most particles were able to pass through, but many were deflected at large angles, and others were actually reflected, just bounced. So I said, oh, why is this happening? So his conclusion, so this is like the setup of the instrument that he used. You see, particles are just passing, but some are being deflected, others are reflected, as you can see. So he said, what am I making of that? He concluded that the plum pudding model is incorrect. The large deflections of the alpha particles are caused by the concentration of positive charges that contain most of the atom's mass. So that's where the idea of a nucleus came in. So that you know what? Most part of an atom is empty space. But where I see the deflections, that's where the mass of the atom is. That's where the nucleus is. And this nucleus contains the positive charges. So he developed a model, an atomic model. So if we talk about those deflections were happening here. The alpha particles coming from here and deflected, others reflected. So his conclusion was that an atom has a denser nucleus, which is a center of positive charge. Electrons move around the nucleus at a distance that is large relative to nucleus radius. So you can see the nucleus radius is small here, and the distance from here to the electrons is really large. So this is the Rutherford's model. So I want you to go over this video, understand this information, and also do the work that I have given with this video, and get ready for class. We'll just continue from here and deal with the hard part of the class. Thanks.